Drop a marble and it speeds up, but drop it far enough and something surprising happens. It stops accelerating. It reaches a top speed and holds it all the way down. A raindrop does this, so does a skydiver. That ceiling on speed is called terminal velocity, and today we will derive exactly where it comes from and how velocity climbs toward it over time. Picture an object of mass m falling through the air, released from rest. Two forces act on it. Gravity pulls it straight down with magnitude mg. Air resistance, the drag force, pushes straight up, opposing the motion. Let us choose the positive y direction to point downward, with the origin at the release point. In that frame, gravity is positive and the drag is negative. Here is the key intuition. At the instant of release, the object is barely moving, so drag is tiny and the gravity wins. But drag grows as the object speeds up, and eventually it fights gravity to a standstill. The drag force follows the quadratic drag law. Its magnitude equals 1/2 times the drag coefficient C sub d times the cross-sectional area A times the air density ρ times the speed v squared. Notice that it grows with the square of the speed. Now apply Newton's second law along the downward axis. Mass times acceleration equals the net force, so m times dv by dt equals mg minus 1/2 times c sub d times the area A times ρ times v squared. To keep things clean, bundle all the drag constants into one symbol. Let beta equal 1/2 times c sub d times the area A times ρ. Newton's second law then becomes m times dv by d, t equals mg minus beta times v squared. Watch what this equation says as the object falls. At the start, v is 0, so the drag term is 0, and the acceleration dv by dt is at its maximum. As the object speeds up, beta times v squared grows, the net force shrinks, and the acceleration falls. Eventually, the object reaches a speed where the acceleration drops to 0. That speed is the terminal velocity, written via infinity. Set dv by dt equal to 0. Then mg minus beta times v infinity squared equals 0. Solve for v infinity. It equals the square root of mg over beta, which is also the square root of 2mg over the product of c sub d, the area A and ρ. This formula predicts the terminal velocity for any falling object. Take a raindrop using a drag coefficient of 0.5 and an air density of 1.225 kilograms per cubic meter. Its mass is about 4 times 10 to the minus 6 kilograms and its cross-sectional area about 3 times 10 to the minus 6 square meters. Put this into the formula with gravity of 9.8 meters per second squared. Evaluate the square root of 2 times the mass times gravity divided by the drag coefficient times area times density. The result is about 6.5 meters per second. Run the same formula for other objects. A hailstone reaches about 20 meters per second, an osprey about 14, and a falling human about 60. Now for the harder question. How does velocity grow over time? We integrate the equation of motion using separation of variables. Start from m times dv by dt equals mg minus beta times v squared. Rearrange to collect the velocity terms on one side and the time on the other. This gives minus beta over m times dt equals dv divided by the quantity v squared minus mg over beta. But mg over beta is exactly v infinity squared, so the denominator becomes v squared minus v infinity squared. That difference of squares invites partial fractions. We split 1 over the quantity v squared minus v infinity squared into 2 simple pieces. The first is minus 1 over 2 v infinity times the quantity v plus v infinity. The second is plus 1 over 2 v infinity times the quantity v minus v infinity. Now integrate both sides. Let velocity run from 0 up to v of t, and let time run from 0 up to t. The right side is straightforward. It gives minus beta over m times t. The left side integrates to natural logarithms. Carrying out the integration yields 1 over 2 v infinity times the following, minus the natural log of the quantity v of t plus v infinity over v infinity, plus the natural log of the quantity v infinity minus v of t over v infinity. All of this equals minus beta over m times t. Combine the two logarithms into one and clear the factor of 1 over 2 v infinity. After the algebra, this collapses to a single clean statement. The natural log of the quantity v infinity minus v of t over the quantity v of t plus v infinity equals minus 2 v infinity beta over m times t. To free the velocity from inside the logarithm, exponentiate both sides. The logarithm disappears, leaving the quantity v infinity minus v of t over v of t plus v infinity, equal to e raised to the power minus 2 v infinity beta over m times t. Now solve for v of t cross multiply, gather the v of t terms and isolate it. The result is v of t equals v infinity times the quantity 1 minus that exponential over 1 plus that exponential. That ratio, 1 minus an exponential over 1 plus an exponential, is precisely the definition of the hyperbolic tangent. So the velocity as a function of time is v of t equals v infinity times the hyperbolic tangent of the quantity v infinity beta over m times t. One loose end remains, the constant multiplying t inside the hyperbolic tangent. It is v infinity times beta over m, substitute v infinity equals the square root of mg over beta. Then beta over m times the square root of mg over beta simplifies. Under the root, 1 factor of beta and 1 factor of m cancel, leaving the square root of beta times g over m. Written out fully, that is the square root of the quantity 1/2 c sub d times the area A times rho times g, all divided by m, so the growth rate of the velocity is set by the drag constants, gravity, and mass. Let us see the shape of this solution. Plot velocity against time. At time 0, the object starts from rest, so the curve begins at the origin. Early on, the hyperbolic tangent is nearly linear, so velocity climbs almost in a straight line, just as free fall without drag would predict. But as time grows, the hyperbolic tangent flattens toward 1, and the curve bends over. Velocity approaches the terminal velocity as a horizontal asymptote, getting ever closer but never quite exceeding it. The object smoothly transitions from accelerating freely to coasting at its top speed. Let us tie it together. Quadratic drag grows with the square of speed, so a falling object cannot accelerate forever. Balance drag against gravity and you get the terminal velocity, the square root of mg over beta. Integrate the full equation of motion with partial fractions and the velocity emerges as the terminal velocity times the hyperbolic tangent of the square root of beta times g over m times t. From a raindrop to a skydiver, that single curve, rising and then leveling off, governs how anything falls through air. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.